Hello everyone, welcome to the lecture 3 of week 2. In this week we are discussing about deep neural networks, so basics of deep learning. So in the last lecture I discussed about shallow neural networks, and this lecture we will discuss deep neural networks. So these are the concepts we will be covering. So what are deep neural networks and how to see them as composing functions, and then what is the distinction between shallow and deep neural networks. Basically, after we had the theorem that any possible function can be approximated using shallow neural network, why do we need them at all, right? So we will try to answer this question. So typically we would say deep neural network is one where you have more than one hidden layer. So in shallow we had only one hidden layer, but in deep neural network we will have more than one hidden layers. Now just like shallow neural network, we will still see piecewise linear mapping from input to output in deep neural network also. And the thing was that as we increase the number of hidden units, even the shallow models, shallow neural networks, they improve their descriptive power. And if you have enough hidden units, they can describe arbitrarily complex functions in high dimensions. The question is, then why do we go for deep neural network? So let us start with a motivation for that. So what I am showing here is a picture from this paper on the number of linear regions of deep neural networks. This paper from NeurIPS 2014. Okay. So what are you seeing? So there are two plots, and actually it's the same plot, and then you are showing the close-up of the first plot. So what is the task? It's a binary classification task. So there are two models that are being tried out. One is a shallow model with 20 hidden units, the solid line. These are the shallow neural network with 20 units. And the dashed line is a deep model with 2 layers of 10 units. So it's 2 layers of 10 units each. Okay. So their parameters are kept roughly constant. Now the question is, which of these models is better at marking the boundary, right? So it's a nonlinear boundary, and you can see, so this is one class, the circles and triangles are another class, blue triangles another class. So if we see, just look at the number of regions, right? So the solid curve is giving me much less regions than the dashed line, right? So dashed line looks like a much better fit than the solid line, and this is the same number of parameters. So a deep neural network is able to give you much more regions than a corresponding shallow neural network will give, right? Even though you can increase the number of units in shallow to make it look similar to this, but this is more efficient to model it using deep neural network, and this is what we will see in this lecture. So now first of all we try to see how we can visualize a deep neural network as composing two different functions, right? Composing two shallow neural network. So you see here, you can think of this as one shallow network and another shallow network, and you are composing them and saying what is y prime as a function of x. So both network 1 and network 2 have very similar equations. So network 1 you have h1, h2, h3. So it can be written as, so nonlinearity, value of theta 1 naught plus theta 1 1 x and so on. Similarly, h1 prime to h3 prime can be written as value of theta prime 1 1 naught plus theta prime 1 1 y and so on. And I can say y is nothing but phi naught plus phi 1 h1 plus phi 2 h2 plus phi 3 h3. Similarly, y prime is phi naught prime plus phi 1 prime h1 prime, phi 2 prime h2 prime, phi 3 prime h3 prime. Okay. So these are two different networks. Now what would be the output of a network by composing these two? So, let us see individually, right. Individually we have done this exercise in the last lecture. So, let us see when we go from output y in terms of input x, right. So, there are 3 neurons and you can see like 3 different regions. So, this is one example. So, you have one region, second region, third region. So, as a composition of these 3 neurons. Similarly, the second network also has y prime as a function of input y. So, you will also have something like 3 regions. Now, what happens if I plot y prime as a function of x? So, y prime as a function of x, and you see interestingly you find 1, 2, 3, 4, 5, 6, 7, 8, 9 regions, right. So, this is interesting. It is not like addition of these 3 plus 3 6, you are getting 9 regions. Now, why is that? So, let us try to look closely what is happening. So, up to this point y is going the entire range of y is being seen, right. So, now what will happen if you plot now y prime as a function of x? Now, you have seen the entire range of y. Now, take it as the input. So, you would have seen an entire range of y prime. So, you see this is exactly this function being denoted here up to this point, because you have seen the entire range of y here. So, you have seen actually this y prime. Now, you are going backwards, right, you are going down, this entire range going down. So, that means it is as if you are mirroring this image. So, you will first go like this. So, it is like a mirror image, but much more shrunk, because this region is much smaller than the other region, right. So, you will see like a mirror image as if you are folding and this, right. And again you are going entire range of y. So, you will see in the positive direction. So, you will again see this. So, you will have this, this and this, right. So, this is some sort of folding effect, and you are seeing this whole thing 3 times corresponding to 3 regions of the entire y, right, in the corresponding to x, and you get 9 regions, right. So, that means, so here how many parameters you have? If I try to look even the bias terms, so you have, so one bias term, so 2 into 3 plus another bias term 4 into 1, 10 parameters, and this is exactly the same thing. So, another 10 parameters. So, you have 20 parameters, while here you have a bias term. So, 2 into 6 plus a bias term 7 into 1. So, 19 parameters. So, that means, so this network, shell network, has one less parameter than a deep neural network, where you are dividing the 6 neurons as 3 and 3. But here how many regions can you get? So, you have 6 neurons, so you can get at most 7 regions. But here we are seeing we have got 9 regions already, and you could have got more if you could have used the full potential, like with 3 neurons you can get 4 regions, right. So, you might have even got more number of regions than 9, but even with 9 you are doing better than 7 regions that you got in the shallow neural network, right. And that is one of the motivation of using deep network than shallow networks. You can get much more regions with the same number of parameters. That is quite efficient. Now, we will try to combine these 2 networks into a single network, right, with the equations. So, we had equation for network 1, network 2, and this is what we had seen, y and y prime in terms of h1, h2, h3 and h1 prime, h2 prime, h3 prime. Now, let me write h1 prime as 8 theta prime 1 0 plus theta prime 1 1 y, because I want to get rid of y now. I want to write in terms of x and hij. So, y is this. So, I substitute for y. So, I get theta prime 1 0 plus theta prime 1 1 phi naught, theta prime 1 1 phi 1 h 1, right. So, I substitute, same here, I substitute for y. So now no, I don't have y anymore. I am writing h1 prime in terms of h1, h2, h3, right? And then I can do further simplification and call it a single bias parameter, and this also I call it as a parameter, right? So I can write it as some constant phi naught, we refine this, plus phi 1 h1 plus phi 2 h2 plus phi 3 h3. We will see how to write it, but the idea is that I can write in terms of h1, h2, h3, right, plus a bias parameter. So this is how I am writing it. H1 prime is A, psi 1 naught, psi 1 1 h1, psi 1 2 h2, psi 1 3 h3, and so on. Right. So I could write h1 prime, h2 prime, h3 prime in terms of h1, h2, h3. And of course, the nonlinearity remains. So then, and then I can say my y prime is nothing but phi naught prime plus phi 1 prime h1 prime, phi 2 prime h2 prime, phi 3 prime h3 prime, right. So now I have got rid of that intermediate y, and I am writing y prime directly in terms of x by using h1 to h3 and h1 prime to h3 prime, and h1 prime to h3 prime are written in terms of h1 to h3, right, like here. Now this is a two-layer network, right. Now how else I can visualize this, right? So if you remember, we talked about multiple outputs, right? Even if you have single input, I can have multiple outputs. How? I can learn multiple functions of the neurons. So I have h1 to h4, so I can say y1 is phi 1 naught plus phi 1 1 h1, so on, and y2 is phi 2 naught plus phi 2 1 h1, and so on. So you still share the joints because of the 4 neurons, but you can learn different functions over these joints, right? So you have different piecewise linear functions for y1 and y2. Now you can consider your pre-activation before you apply your ReLU here. So this pre-activation is nothing but phi 1 naught plus phi 1 1 h1 plus psi 1 2 h2 plus psi 1 3 h3, and this actually resembles this equation, right? This and this equation look very similar. So this is nothing but as if you are getting one output, right? So this is your one output, second output, third output. So pre-activations, you can think of pre-activations as your outputs, multiple outputs, and then you are applying the nonlinearity. So this ReLU function, right, and that is giving you h1 prime to h3 prime. Okay. So now you can do the exercise that we did with shallow neural network. So what we had there, so you had, so let's say this is your psi 1 naught plus psi 1 1 h1 plus psi 1 2 h2 plus psi 1 3 h3, and this is for psi 2 naught and this is psi 3 naught. Right. Let's say I have 3 different mappings. Now you apply your nonlinearity. So I apply ReLU, so that means the negative part will go away, and this will be converted to 0. Same here and same here, right? And you see now you have got quite a few regions, 5 regions here, 5 here, again 5 here, and then in the final output I will combine h1 prime, h2 prime, h3 prime with some multiplications and add another offset. So let's say this is my multiplication, looks like negative, and these two are positive multiplications, and then I add to get the final output, and you will get quite a lot, many regions here, 1 2 3 4 5 6 7 8 9 10 11 12 regions. Right. You got 12 regions with a simple two-layer neural network, where even if you would have composed the neurons together, you would have got at most 7 regions, right? 3 neurons plus 3 neurons, 6 neurons, you would have got at most 7 regions, but now you are getting 12 regions already. Yeah. So this is much more efficient to get regions through deep neural network. Okay. So at this point, this is simply a one-layer network with 3 outputs, but then by applying nonlinearity, you make it a two-layer neural network, right? and this gives you the further advantage of using multiple layers. So, what are the hyperparameters I use? So, what is the depth of the network? So, I can use k layers. So, I just talked about 2 layers, but you can use much more layers. And how many neurons do you have per layer? So, let us say you have dk hidden units per layer. This is the width of the network, how many neurons you are using in each layer, and then depth is the number of layers, right. And these are called hyperparameters. So, they are typically chosen before training, and you can vary these hyperparameters and see what is the impact on the development set loss. And this is what is called hyperparameter optimization, like what is the optimal width of your network, what is the best depth of your network to achieve a good performance on a particular task given some data set. Okay. So, now because as you go more and more into depth of the network, it will become difficult to keep working with theta 1 and psi 1 naught and all. I mean, how many more symbols would you really invent, right? So, you can put some nice notation. So, you have 3 neurons. So, put them as vector h as a nonlinearity over theta naught plus theta x, right. So, this is one way of writing this whole equation. Similarly, this you can write as h prime as nonlinearity over psi naught plus psi h, right, where psi is a matrix here, 3 cross 3 matrix. So, here input was a scalar, but now for the next layer the input is not a scalar, the input is h1, h2, h3 from the previous layer. So, this becomes a matrix, and then finally, because your output is scalar here, so you have phi naught prime plus phi prime h prime, where h prime is this one, right. So, this becomes much more manageable, this notation. Now, we can even simplify that further, saying okay, so we have the bias terms across different things, right, and then there are some weight parameters. So, I can use some consistent terminology for these, saying that okay, for the first layer I will call it h1, right, the activations, second layer h2, and finally, I will call it my output y. Now, every time hi I will say h relu over beta I minus 1, that is you start with beta naught plus omega. Omega is your parameters for the main weights, right, the bias, and these are your weights, right. And first time h1 you will get beta naught plus omega naught input, next time it will be beta 1 plus omega 1 the previous activations h1, and so on. For any number of layers you can keep on reusing these notation. You can say h l is a beta l minus 1 plus omega l minus 1 h l minus 1, right, for any nth layer. Finally, the output will be the again the bias that you need for that plus omega 2 h2, because you only had omega 1 before. Right. So, this is how you can denote much more in a much more simple manner than inventing new set of parameter notations for every layer. Okay. So, bias vector and weight matrix is what is needed for going from one layer to another layer. So, as an example, so you have here a 3 layer, right, 3 layer deep neural network, hidden layer 1, hidden layer 2, hidden layer 3, and here each layer even has different number of neurons. So, hidden layer 1 has 4 neurons, 2 has 2 neurons, and 3 has 3 neurons. Your input is 3 dimensional and your output is 2 dimensional, right. So, what are the parameters do you need? So, going from input to the first hidden layer you need, so also take the bias into account. So, bias would be just the dimension of the output for this. So, that is 4, bias will be 4 dimensional, and the weight will be 3 cross 4, right. So, a 4 cross 3 matrix. Next you go from layer 1 to layer 2, bias will be the dimension of the layer 2. So, 2 dimensional, and the weight will be 2 cross 4. Same third layer 3 dimensional, and the weight will be 3 cross 2. finally output are 2. So, your bias is 2 dimensional and the weight matrix is 2 cross 3. Right. So, that is how you can even count the number of parameters, right. So, you can just count the biases are 4 plus 2 plus 3 plus 2 and the weights are 4 cross 3 plus 2 cross 4 plus 3 cross 2 plus 2 cross 3. That many weights and biases do you really need here. Okay. So, now let us just come back to this comparison between shallow and deep neural network. So, what is their in terms of their ability, like is it that the deep neural network can approximate much more complicated function? It is not like that, because both are obeying the universal approximation theorem. So, any complicated function you can use shallow networks, you can also use deep neural networks. But one may argue that right, we have learned one layer is enough, and deep networks could arrange for other layers to compute just the identity function, right. So, if one layer is enough, maybe even if you are using deep neural network, they will just learn identity, right. So, that way they also follow the universal approximation theorem. Now, what is interesting in terms of difference is the number of linear regions that you get per parameters. So, deep neural networks can actually create many more regions per parameter than the corresponding shallow neural network. So, this is again a very nice plot depicting this. So, k here is the width of the network. So, k is equal to 1 is just a shallow neural network, and we are going up to k is equal to 5, a deep neural network with 5 layers, right. So, here you are seeing parameters, right. So, input dimension here, input dimension is 1, here input dimension is 10. So, what do you see, right. So, even if you have 10 hidden units per layer, that means roughly 470 parameters, little less than 500, you get 161,501 linear regions, huge number of regions, right, with a deep neural network. Now, with the same parameters, if you tried a shallow neural network, you would have achieved something close to 100 plus regions, right. Actually, little more, because if there are 500 parameters, you can easily get 501 regions and so on, but will still be less than 1000, right. And here you are getting some 161,000 regions, which is quite many compared to what you were getting with shallow neural network. So, this gives you some idea why this is so important. And as you increase the number of input dimension, we saw the number of linear regions also increase, right. So, this happens here if your input dimension is 10. Now, you are getting roughly like 10 to the power 40 linear regions, right, with 50 hidden units per layer, right, like 10 to the power 40 linear regions. So, huge. So, number of linear regions that you are getting because of the combination of input dimension and the deep layer becomes a lot, right. Another very interesting thing that has been seen is that it's much more faster to fit a deep neural network than a shallow neural network. So, again this picture is showing you 4 different training scenario for MNIST 1D data set. So, there were 4 fully connected networks, they were fit to 4000 examples. Now, they were 1, 2, 3 and 4 layer networks, and they had some number of hidden units such that the final parameters are roughly same. You see, they are like 15,200 in that range, that many parameters. They had fixed the number of parameters, but the layers are different, right. Now, you are trying to see how many epochs, that means iterations over the entire data, do you need to get a very low training error. And what you can see, if you have 4 hidden layers, the number of epochs are much smaller compared to the other networks where you have just one hidden layer, right. So, you need much more epochs compared to when you have 4 hidden layers. So, that is another dimension of efficiency, that they also are able to converge faster. They are able to you can fit deep neural network much faster than a shallow neural network. So, these are some evidences of why deep neural networks are preferred over shallow neural network, and we would see we will typically use these deep neural network with multiple layers for different architectures. Okay. So, you can go through the chapter 4 of our UDL book to learn more about deep neural network, and we will continue from here in the next lecture. Thank you.